So previously we talked about the basics of recursion. We talked about some of the fundamentals and some ways of thinking about problem solving recursively. So namely, we had things like the recursive case, the base case, and we talked about how we could do things like adding numbers, how we could do factorial or Fibonacci numbers using recursion. And we've seen some examples of programs or even algorithms written in pseudocode for doing such things. And we sort of made a presumption about how it works. So now I got to talk about how it works. because so how does it work? That's a very good question. How does it work? So recursion relies on the call stack. So if you've never heard of this idea of a call stack, we're going to see an example of what I'm talking about in a moment. I'm not going to go overly technical about all of the parameters, one of the records or activation records or stack frames or call frames, what would look like. I'm just going to keep it higher level here. This is sometimes also called the runtime stack. And you might ask, Dan, what the heck is this thing? The call stack is used to store data. That R's looking a little sad there. To store data needed for methods or functions while the program is running. This includes the following. So some things that are known. So this is stuff that gets stored in the so-called call stack. So things such as the parameters of calls. So I'm talking about function or method calls. They're local variables. So every one of these calls, I want to be able to keep track of the local variables associated with that call. I also want to have it so that I can keep track of the return value. And of course, I want to know a memory address for where to return to continue executing when I'm done executing my function or method. Memory address of where to return. To continue executing. So just to be very clear, whenever a function or method is called, so whenever a function or method, whichever is your favorite taste of flavor, whenever a function or method call occurs, an activation record, which is sometimes also called a stack frame, or call frame, an activation record is created, which has this information, is created and pushed onto the call stack. So I must stress that when you are executing your programs during runtime, there's going to be what we would usually refer to as the heap. So you have heap memory. There's also stack memory. So this call stack is just a part of the runtime memory. So what am I talking about here is that every time you make a call or you call a function while executing a program, it goes onto this so-called call stack. So a stack, just for context for those that aren't familiar with what a stack is in data structures. So a stack, you might think of it like a stack of plates, for example. So a stack of plates may start off as empty, and then I could push plates onto the top of the stack. These might represent different objects. In this case, they would be representing activation records. So when a function finishes executing, it gets what we call popped, or it leaves the stack. So it gets popped from the stack. So it gets removed from the stack. But it only is the thing that's occurring on the top of the stack. So for example, say at the beginning of execution, your typical programming language, you'll start off with a function or method call to some main function. And then this calls some other function. Well, that creates an activation record. It gets pushed on the top of the stack. The reason why we have to keep track of things like the memory address toward a return is that information helps us get back to when this function finishes executing, gets popped or leaves the stack. It tells us where to continue executing from for our function here. But it also, we could pass along the return value when we're done. So the whole idea is that every time I make a function call, it gets pushed onto the top of the call stack. This call stack will, each time when I push something to the call stack, whatever's on the top of the stack is what's currently the function executing. So please just keep that in mind. So the big thing I really want you to know about is that we can push elements onto the stack, but they always go on the top of the stack. But you can also pop elements off the stack, which get removed from the top of the stack. Everything is handled on the top. This is in contrast, by the way, to something called a queue, for which what happens is when you do end queues, it goes onto the back of the queue, just like you would be waiting in a line, hence its name, but you leave the front. So just please keep that in mind when we talk about the call stack, because it's just a stack. It's just one for these activation records. And I must stress, this isn't something special just for recursion. This is how your programs execute, is that whenever you call a function, it goes onto the call stack. Just recursion is just a special kind of function call, right? You're just calling a function with the same name, maybe different parameters. So the big thing I really want you to know about is whichever function, so this is referring to its activation record, is on the top of the stack, is actively being executed by the computer. Function calls, when you're using recursion, are no different than just any old function call. Please remember that. There's nothing special when you start thinking about it like that. It just creates activation records. They're just functions with the same name, right? So remember that the order in which we perform function calls may matter, so please be very careful about this. So that's something that you'll explore more if you play around with some more problems that involve recursion. So I thought I would do an example, just kind of walking you through this process of seeing how one of these call stacks would look. So I'll mention just here that order of calls may matter. So this is just a caution. So let's go through an example here. Previously, we had seen how we recursively could add numbers 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to some positive integer n. So suppose that we were to consider rec sum of 4. So I just want to show you how this would go through, considering that we've seen in a previous lesson, we talked about what this would look like as an actual function. So how would this work? Well, your initial program, when you execute it, you'll start off with the main function, right? So you're going to have a call stack. So here's your call stack. And it's going to have, it starts off by executing main. And then somewhere in the main, it executes rec sum 4. So when it calls rec sum 4, it passes along. So a part of this, it creates an activation record on the call stack. They'll include the parameters and any of the local variables as they get allocated. And of course, the return value as well. And of course, it'll tell us where to go when we're done. Right now, I don't know what the return value is. But let me walk you through step by step this process. So remember that right now, rec sum 4 is on the top of the stack. So are we going to finish the main function? Not until we're done executing rec sum 4, right? So to execute rec sum 4, because it is in fact greater than 1, that means that to answer this question is the same as me asking the following. It's 4 plus rec sum 3, right? Well, to get the answer to this question requires me to carry out rec sum 3. So I call rec sum 3 on that line if you take back and look at that function. Creates an activation record for rec sum when we call on rec sum 3. The input would be 3 in this case. We don't know the return value quite yet, but we have an activation record. Is it going to continue executing rec sum 4? No, because we don't know the answer to rec sum 3. It's called rec sum 3, so now we've created an activation record. Now what's currently going to execute is rec sum 3. But now rec sum 3 is going to attempt to answer the question by saying 3 plus rec sum 2, right? So it's 3 plus this function call. So remember that returns a number, but to complete this operation of this addition, I need the answer of rec sum 2. So when I'm calling recursively rec sum 2. So I create a new so it creates an activation record, rec sum 2, for which its parameter is 2, for n is equal to 2, and we don't know the return value quite yet. So do you notice that I'm not executing any one of these down here, right? It's whatever's currently at the top of the call stack. But now I'm going to call rec sum 2. So now rec sum 2 says, okay, well, since n is greater than 1, I get 2 plus rec sum 1. It's rec sum of 1. Well, now notice I'm going to make a function call. So now I'm calling rec sum 1. The input is 1. Return value, I don't know quite yet. But now here's where it's nice. We have this is the base, this is going to execute the base case, right? So this one here says the answer is 1, so it returns 1. So it says, okay, the answer is 1. So now I'm going to finish. That means just like my plates over here, rec sum 1 is completed. It's going to be popped off the stack. Then rec sum 2 is going to be executed. Again, remember, it's going to go back to where it was halted at that point, back to the memory address for which that operation was occurring for completion. So now passes along the 1, pops this, and now this is the top of the call stack. Now I have a 1 plus a 2. So the answer here is 3, right? So this is giving me back the 1. This gives me back 3. Now I'm finished executing recsum 2, right? So I pop that off the stack. I give back 3. Because now that's the answer to this. We have 3 plus 3. Well, now 3 plus 3 is 6, right? So I return 6. Pop it from the top of the stack. So we pop the stack. Now I got 4 plus 6. We complete. 10, we return 10. And we pop the stack. And now we're back to the main function call. And for example, if I had a print statement in here, I could print out 10. So this, then of course, when the main function finishes completing all of its operations, this gets popped from the stack and the execution of the program completes. So this is an example of how a program would be executed based on function calls. So the call stack manages which function is currently executing and how we pass along the information or data from one function call to another. And recursion naturally reflects in such a mechanism like this. But remember, this process we just did here with the call stack, it's no different than any other function calls. Just what makes this different is that the functions have the same names. Okay? It's just solving a problem by taking, so I know how to solve a bit of it. I might pass along the rest of it. Sorry, I'm getting really excited here. I'll pass along the rest of the problem because I don't know how to solve it. I'll pass along recursively to somebody else to answer the question. But the point is that how it works, your best friend's the call stack.